Hello, everyone, and thank you for joining us today for this webinar, How to Build the Megaservices. I'm Nidhal Daghrir, your host for today's webinar. I'm Project Director and Mind7 Consulting, and I'm working since 2016 on supporting our clients who are developing agile and reactive platform. Today, I'm delighted to have Hugh McKee, a developer and microservices reactive platform advocate, who will be presenting and demonstrating how to build megaservices. So I'm gonna let you maybe do a little presentation, Hugh, and maybe start the presentation after that.
Okay, thank you, Nicole. Hey, hello, everyone, again. Thank you for joining us today. I hope this will be interesting to you. It's definitely about microservices, and that's the area I focus on at Lightbend a lot, building microservices. And one of the areas that we focus on with our technologies is building high performance microservices or high throughput microservices. So this is what this session will be about. So should I go ahead and start going through the material? We're all set?
Yeah.
All right, thank you. So let me just get going. The rough agenda in what I'll be talking about today, of course, is what I mentioned about high throughput microservices. And I'll be focusing on things like how, to do that, you need to build things that have low latency and low overhead so that you do get that high performance. So a fundamental approach that we use, and what I'll be showing you, is implementing these things using stateful microservices, not stateless microservices, which is a very common. And the foundation technology for doing this is what I call globally unique persistent objects, and the short name of them is entities. An entity is a thing, say for example a shopping cart or some physical thing in the real world, an IoT device, a shopping cart, a user, something like that, and you have a back-end system that is managing those things. So these globally unique persistent objects is a core characteristic of what I'll be talking about, and again, it's all stateful. So in the presentation, I have some slides, some material, mostly visual stuff. I like to do things visually instead of a bunch of words on slides. But more importantly, I've got some demos that I'll be showing you. That I'm also going to be sharing with you the GitHub repos for these demos, and all the source code, everything that I'm showing you, you can take and install and do yourself. I wrote these demos myself, so they include the backend Java code to do things on the backend, and then some JavaScript to do some kind of this fun front end stuff. And then I'm also going to be showing you some of the code examples of the code that's running behind the scenes in this talk. So I'm just going to start really quickly by showing you this first demo application. I call it Where on Earth, and the reason is that it's the user interface for this demo is a map-based user interface, and it's a kind of an IoT type of a demo. It's so I'm simulating IoT devices, but there's a simulator service, and there's also an IoT microservice running here. This demo is live. It's running in Amazon, in Kubernetes in Amazon, using some Akka microservices. So the way this user interface works is if you can see the map, there's markers on the map, and these markers indicate where IoT devices have been distributed at various geographic locations around the world. So if I zoom in, for example, on the map, and this is very much like a Google map type of thing, I can zoom in, say, of course, I'll zoom into the Paris area. And as I zoom in, you can see that there's these markers change to kind of highlighted regions on the map that show where devices have been created. And there's a lot of them. In the bottom right, it's showing that in view here, there's around 11,000 individual IoT devices that have been created. Worldwide, right now, when I was at the world map, there's around 230,000, 236, I think, thousand devices worldwide. The data that we're seeing here, though, on the screen is coming from the backend microservices. And this zooming and everything is, being supported by of course, the front-end JavaScript, but the JavaScript is constantly talking to the backend microservices to get this information. So you can zoom in. If I zoom all the way in, you can start to see where devices are located. So these little, hopefully you can see it, but these little crosshairs show where individual devices are at. So I'm zoomed as close as I can get to the map, and at this zoom level, each of these regions, as I move the mouse around, covers. The way this app works is there can be one IoT device in that region. Of course, this isn't practical because you can have lots of IoT devices, say in somebody's home, for example, but this is just a demo. As I zoom out, it stops showing individual devices and it just starts to give me device counts. Now, it's interesting with these maps, and this is a map from, it's an open source project called OpenStreetMaps. I think it's openstreetmaps.org, you can find it online. Excuse me, but in any case, when I zoom out, there's zoom levels, and every zoom level, the map zooms by a factor of 4. So at the lowest level, as far as devices, I can see one device in one of these regions. If I zoom out, the region can hold up to 4 devices. If I zoom out another level, it can hold 16. So I can zoom. The reason why I wanted to use this demo or this map UI was because not only did I want to say have individual IoT devices, but I wanted to have a platform for testing, creating lots of IoT devices. So as an example, I can create a bunch of devices here. And if I zoom in, this will create 16 devices. So if there's some commands that I can do that for doing this, and when I said I want to create some devices and I select a region on the map and I click it, and that sends a request to the backend system, and it just created 16 IoT devices in this region. So that's not very exciting. I want to do a lot, so I'm going to zoom out, and I'm zoomed out to a level that if I do a create, it's going to create 1,000 IoT devices. So I'm going to select this region that currently has 16 devices, but I'm going to say, just fill it up with, it's actually 1,024. So I click, it sends in a request, and then you can see it's already done. It just created 1,024 IoT devices. Now what happened was, this request went to one microservice that I call a simulator. And that simulator took that single HTTP request and exploded it into 1,024 gRPC requests that are sent to the other microservice, because I want to feed traffic to the second microservice and put a load on it. So I just sent 1,024 gRPC requests. I could reconfigure this thing to do HTTP if I wanted. But I put a load on it and it triggered a lot of activity. Now, if I zoom out even more, this is at 4096. So if I do a create here, I'm sending in a request and it's going to trigger creating 4096 devices. So you can see it's filling up the region here. Now it's running at 1,000 per second, but it did it pretty quickly. So, but again, very easy to put a load on this microservice. And I can watch it with performance tools. I can just see the response time here. And knowing a lot about what's going on behind the scenes is interesting. So I wanted to make this demo kind of fun and interesting with this user interface, but also give you something if you're really interested and want to dig into the code and really understand what's happening behind the scenes and see how this system is built to handle, fairly, non-trivial performance loads, and you've got this thing to play with. So that's how this demo works. And I'll show you the demo again in a little bit. Now, back in the slides, I have the title of this presentation is a bit provocative. I'm calling it a mega service and high throughput microservices. I wanted to use it to kind of capture your thoughts in a way about this. So, so this definition of what's a mega service is a microservice capable of processing millions of logical operations per second, which is an insane level of performance. But I wanted to really kind of highlight the fact that we're heading in that direction, that you guys are building systems that are every year taking on more and more load, more and more traffic, and we just need the tools to be able to do these kinds of things. So I kind of played with this a little bit. Instead of calling it microservice, which kind of implies reduced complexity and focus on a specific task, I wanted to change the prefix of the name to something that denotes performance. So just playing with it, a Deca is a service that does tens of logical operations per second, hecto hundreds, kilo thousands, which is pretty much at the high end these days. But then mega, we're hearing more and more about people building systems that are processing massive amounts of data very, very quickly. So, and these logical operations are really kind of business-oriented operations, so it's not like a database operation or something like that. I wanted to make it a little bit bigger and more intuitive in scope. So it's like adding a device to a shopping cart. I'm sorry, adding an item to a shopping cart, or changing an item quantity in a shopping cart, removing an item from a shopping cart. These are all logical operations. Creating an IoT device, changing the state of an IoT device. Those are all logical operations. And of course, these operations can involve multiple things that the system has to do in order to process these logical operations. Like it could involve one service invoking processing on another service. It could involve, certainly, of course, non-trivial database operations. It could also involve accessing external services via APIs or something like that. So it's pretty, these logical operations are pretty inclusive into types of things that actually happen internally in the system itself. So like I said, this demo application is built with two stateful microservices. These microservices, the trick with stateful is that you still can do it where the service itself can scale. These are running in Kubernetes. If you're familiar with Kubernetes, Kubernetes is a great platform for running many things like the same, like with a stateless application, you could run multiple instances of a stateless application very, very easily with Kubernetes, where you can do the same thing with these Akka microservices, where you can run multiple instances, but they form themselves into Akka clusters. So these clusters can scale up and down, so each microservice can scale independently, which is what you want, and they can scale back independently. When something breaks, like say one of the instances of the scale, like in Kubernetes, things run as pods. If, say, a pod stops for some reason because something breaks or a network breaks or something fails, in the infrastructure, it's not an issue, because not only does Kubernetes heal things, but also Akka helps heal things as well. So to kind of show you that, I want to show you a second demo that gives you a little bit more insight into what I'm talking about inside of these services. So the second demo is also running a couple of Akka microservices in Amazon, in Kubernetes. And this is exactly what the other demo is doing that I just showed you, the map demo that I call Where on Earth, but it's doing it at a much smaller scale. So what this represents here is a running single microservice, and it's kind of showing you the inside of these single microservices. So the three big circles represent three pods, three nodes in an Akka cluster. So a node in an Akka cluster is a JVM. In Kubernetes, a JVM runs in a container, a Docker container. The Docker container runs in a Kubernetes pod. So it's kind of a, JVM is in a container, containers in a pod, pods run in Kubernetes. So it's like running 3 JVMs on 3 different virtual machines, for example. So that's what these big circles represent. They also represent HTTP endpoints where there's HTTP traffic coming in from the top right here. So these lines coming in from the top right are live HTTP requests that are being fed in through another simulator into this microservice example. And then the lines you can see are coming into a individual JVMs here, nodes in a cluster. And I can turn off some of these lines so it's not kind of a scramble. So we're just seeing the kind of the message tracing that's coming into one of these nodes in the cluster. So the reason I wanted these lines to come in, these are HTTP requests coming in from the top right into this node circle. And then the lines coming out of it are going to these circles on the perimeter. And these are the stateful persistent objects called entities. These entities are the place where your business logic runs. So, say if this was a shopping cart application, these entities would have the business logic. It's just a class. It's an instance of a class. That's why I call it an object. These classes are getting, incoming requests through a method, and those requests are things like add item to cart, remove item from cart, change the quantity of an item in the cart. That type of thing. That's what these things do. But these entities are instantiated across a cluster. The HTTP messages coming in to this one HTTP endpoint are then routed across the cluster to specific entities, because these requests are coming in are for specific entities. So that the routing is being handled by Akka here. This is what allows us to make these entities stateful. Meaning that when an entity receives a message, if it's not instantiated, the system instantiates it and it populates it with its data. Now the entity is stateful. It doesn't have to read from the database anymore. It's got its state in memory. And every time it receives subsequent messages after that, it's going to not have to in a stateless system, and I'll show you this towards the end of the presentation, but in a stateless system, you constantly have to reread the state from the database, bring it into memory, do your computations, and push your changes back down to the database. In this approach, because it's stateful, we're eliminating having to constantly reread the data from the database. And the trick to this whole thing is this ability to route messages to specific entities across the cluster. Now, one of the things I want to show you though is to show you what happens when a failure occurs. So say I'm highlighted just these entities here, and I highlighted by clicking one of these green circles, and these green circles are called shards, and they're also these are Akka actors if you're familiar with Akka and the actor model. But these shards are used to distribute load across the cluster. That's what their job is. So what I'm going to do is I'm going to stop this node in the cluster, this node 76, and I'll show you what happens when a failure occurs. So I can stop it by clicking on it up in the top left. So now we're down to 2 nodes, and then what we should see in a moment here is there's the red shard. The red shard, Akka saw that we lost the node in the cluster. We're still receiving messages for these entities that belong to the shard. Well, Akka brought that shard back to life in another node in the cluster. Now, while I was talking, Kubernetes saw that one of the nodes stopped in the cluster and it restarted it. This is what Kubernetes does. So this is kind of the reason for this demo is to kind of show you the relationship between Akka and Kubernetes here. Kubernetes is handling things kind of at the pod JVM level. It's kind of at the coarse grain. If the process stops, if the JVM stops, if the container stops, if the pod stops, that whole containerization that happens within a pod. When one of those instances stop and you've told Kubernetes, hey, I want to run 3 of these things, it will react to that and start things up at a coarse grain level. It'll restart the process. At a fine grain level, inside of those processes is what Akka is handling. So it's handling the management and the distribution of individual entities across the cluster. So that's kind of the mechanics. The other thing I do, if given more time, but I think for the sake of time I won't do that here, is I show scaling up. Say simulating. I can simulate increasing traffic and then increasing the number of pods at the Kubernetes level, and then showing how the workload gets of these entity actors gets redistributed across the cluster. But also, again, this demo is, the source code is available, the JavaScript, the Java, everything's available. The READMEs are there to help you with the installation and setup of these demos. So, if you want to try it yourself, I'll give you the links at the end of the talk. So let me go back to the deck here. So now I want to kind of get into how these things were built. How do we get the performance, the scale, the durability, that type of stuff. So I want to start out with this graphic here that shows you the different things that, as a developer, I had to implement to make these demos work, and then you would have to implement if you were to use this to build your own microservices like this. But there's really a set of fairly simple components. So the first one is there's this handling the incoming requests to the microservice. I call it kind of at the edge of the microservice. So it could be incoming HTTP request or gRPC request, whatever is the requirement for the service. So that's one. The second one, this is the entity. This is the business logic. This is the blue circles that were on the perimeter of that demo I was just showing you. You write the code for that. Now, what you don't write is the routing of messages from the edge to individual entities running somewhere in the cluster. That's not code that we have to write. That's something that's being handled by the Akka system itself for us. And then the third one is that there's a process for taking data that these entities produce and making them queryable. And I'll show you a much more detailed example of what's going on there in a few minutes. The fourth one is it's not unusual for microservices to be consuming messages from some kind of a topic, and maybe those incoming messages are being handled by entities to process them. And then the fifth one is finally pushing data out to a topic. That a microservice might be pushing things out, communicating out to some kind of a topic in some kind of a message bus, again, like Kafka or something. So that's really kind of it. There's these kind of 5, general areas that as developers we focus on, and that's kind of the approach for building these kinds of microservices. So I want to show you a bit of the code and what's behind the scenes here. So the edge part. I use this diagram here often to talk about command query responsibility segregation, CQRS. You may have heard of it. Maybe some of you are already using it. And it's a very event-oriented approach for doing things. So it's CQRS and it's event sourcing. So you often hear about event sourcing as CQRS or CQRS and event sourcing. But this diagram shows you some of the mechanics of it. So I'm going to walk through this diagram, because basically the code that is implemented is really addressing the different parts of this flow here. So the first part of the flow where this red arrow is at that I want to talk about is the client, say, sending in requests. Now these requests come into the service interface, and the service interface basically is taking those requests. And there's 2 fundamental kinds of requests that these services take when you look at building services using things like event-oriented types of microservices. So one of the things, the inputs could be our incoming requests are considered to be commands. And a command is a request to perform some kind of a state changing operation. So for example, add an item to a shopping cart. Add an item to a shopping cart changes the state of the shopping cart entity, right? But the command is an intent to perform this operation. It's not, it hasn't happened, something that hasn't happened yet. So the service interface is taking in these external requests and building up or sending off commands, add item, remove item, change quantity, those types of things. Another type of request could be to perform some kind of a query operation. So in the code, I want to show you the code for this, and I'll show you the HTTP server code. So this is the Where on Earth source code project. Again, this is all GitHub. You'll have the link for it at the end. And this is the HTTP server that's receiving requests. And one of the requests that can come in, defining a route here to handle various types of incoming requests. You can see some of them for JavaScript and the HTML and those types of things. But the one I want to show you here is this handle telemetry action post. So that goes off to a method here, this handle telemetry action, and it calls this method here, submit telemetry request. And I want to focus you on this line here, 102, because in this, this is where the routing happens. The incoming request, I pull what's called an entity ID, which is like the primary key, out of the incoming request. I build what's called an entity ref, which is kind of like an entity URL, using some APIs that from Akka. And then in this one line here, I say entity ref dot ask. That dot ask is saying I want to send this object as a message to a specific entity somewhere in the cluster. This is all I have to do. I don't know where this entity is. I don't know if it's currently resident somewhere in the cluster or not. I don't care as a developer. All I'm doing is saying, yep, I got this message and I need to send it to an entity. So 3 lines of code and off it goes. So that was the incoming requests into those big circles, and then from the big circle, the lines coming out, going off to those smaller blue circles on the perimeter of the diagram. So this is the code that triggered that, sending the messages off. So all the routing happens in the Akka code itself. That's it. So the next part is the entity. So in the entity, this is where the command was sent from the service interface off to the entity. So the entity in CQRS and event sourcing is called the write side, where changes occur and you're writing data, you're producing data. So as I said, a command is an intent to perform an operation that hasn't happened yet. The write side, basically, which is the entity, receives that command, validates it, is the command acceptable given the current state of the entity and other business rules, whatever, this is very unique to the problem that you're coding for. But you validate the command, and if everything's good, what happens is an event object is created, and that event object is persisted. So the events are historic statements of historical fact. It's something that's happened in the past, like item added in the past tense. It's something that's already happened. So the command said add an item to the shopping cart. An event says the item was added to the shopping cart. Now the big thing with event sourcing is that we're not updating some kind of relational model, say in a database. What we're doing is we're simply writing events to what's called an event store, or an event log, or an event journal. These things are known by many different names, but the simple fact of the matter is that this is a data structure. It could be a simple relational table, it could be Cassandra. It's kind of a key value thing. There's a key that has the, say the entity ID, maybe a sequence or a timestamp or something like that. and then the contents of the event itself. That's the value. But the part of the reason for doing this is fast. All we're doing is inserts. There's no updates, there's no deletes. You're always inserting more and more data. So even the fact that, say, you're removing an item from a cart, you're not updating or deleting any data. You're just adding to a journal, like an accounting journal. In accounting journal, you never erase anything. You're always making adjustments to the journal. Well, that's exactly how these event stores work. That's why they're often called event journals also as well, because they perform just and act just like a journal. So, but performance is fast. It's a single simple insert. That's it. No, and very little reading from this. It's not built for queries. It's built for writing. That's it. That's what's happened. So let's take a look at the code for this. Go back over to the code, and this is the code. It's called device, because this is an IoT device type of application. So in this case, when the commands are received from that, the ask that happened on the HTTP server side, here's a command. It's like, telemetry message, create command. When I created like 4,000 devices, so 4,000 of these commands were handled by 4,000 different entity instances. So if I go to this create command method, it does its work. And in this line here, 68, you can see that it's doing a persist. And it's creating a new, the command's coming into this method, but it's creating an event, device activated, again, in past tense. It's something that's already happened. So we're creating a device activated from a telemetry command. And then it's persisted, which means that's where the operation to insert the data into that event log happens right here. And then if everything's good, we reply back to the sender, and the response goes back to the HTTP, the edge, and we send the response back to the client. And that's really all that's involved here. So the routing, again, the miracle of getting this message to this specific entity could be in another, one JVM is where the HTTP server is running, and another JVM running, and another part of the network is where this entity is running, and all that routing is being handled by the system. But this thing is also stateful. Once this entity is brought into memory and is actively receiving messages, it's going to stay in memory until it stops actively receiving messages. And once it doesn't receive any messages for a while, then specific entities will stop themselves, basically. They'll remove themselves from memory. Pretty straightforward. Oops. So let me flip back over. And then the final piece of code I want to show you is, I showed you in this diagram that the entity created these events and stored these events, but these events aren't very queryable. So in order to make this data queryable, there's this process of going from this write side to a read side. But this is happening in the background. It's not happening within the same transaction that occurred to write the event to the database, which is very quick, very minimal transaction. So in the background, what's happening is there's something running. It's called an event handler that's taking those events as fast as possible and projecting that data into some kind of queryable views, queryable tables. So that's what's happening next. Then the data here is then stored in a way that's optimal for the kinds of queries that this service needs to perform. So that's what, the red arrow pointing at the read side here is what we're looking at. And just to kind of hopefully help with this, because I know often this is a pretty new concept, got another diagram here that I'm trying to get this point across, is that, I got these phones, devices that are sending in commands, this is kind of over time, and it's not in any way applying rate. It's just implying that there's a stream. Think of a device as sending a stream of commands into your application. So these commands are flowing in from whatever the users of the device bang on the glass on the screen to make something happen. But they're being processed by these command handlers, these entities, and then the processing, as we've talked about, results in events. And I just think of an event store as this kind of never-ending stack of events, one event piled on top of the other. It's just this simple, very simple key value data store. So that's the processing flow. And the big thing here is the command comes in, it gets processed, the event gets stored, and we go back to the user. So we go back to the client doing the least amount of work is kind of the idea here. So we can get, we have fast response to the client even under heavy loads. But then behind the scenes, I'm going to kind of zoom in here, are running in the background. In general, there are these things, they're event handlers. So these event handlers are reading by offset. Each one is running independently. Outside the transaction where the events were created, that's an important point, but they're reading as fast as possible from the new events as they're added. And they're doing something with these events. So I've got 3 examples here. One example is these events are being pushed, one event handler here is pushing messages out to a message bus. Another event handler maybe is doing what I'm talking about right now, which is taking events and making them queryable, doing some kind of processing to update tables and whatever in some kind of a database. And a third event handler, just for the sake of an example, say is pushing the same events out to some kind of external API. So these event handlers could be doing filtering and manipulation and processing, whatever. Each one of these are different. But also more importantly is things like, say this external service is offline for some reason. We can't talk to it right now. But the users are still, busily adding, sending in commands, which are producing events. So the microservice itself is still servicing the users. It's still working is the main point, regardless of the fact that say this external service is offline at the moment. Well, that's no big deal because these event handlers are built in a way where when they can't do their work, it's kind of a circuit breaker type of implementation where they'll back off, but they'll keep occasionally retrying to perform the operations they're supposed to try. So when this external service comes back online, the event handler picks up where it left off, and maybe now it has a backlog to work through, but it'll work through it as quickly as possible. So this gives you a form of reliability as well as performance, because the users aren't paying for this overhead. This is stuff happening behind the scenes. So it's another feature of trying to build highly performant services like this. So one final look at the code. Oops, let me go to the code that does this. So this is an implementation of it's called a projection. It's called an Akka projection. But these Akka projections are fed events. There's different ways to implement it. You can implement a projection where it's fed one event at a time. In this case, because of the way this application is written, and I wanted it to be fast anyways, there's another approach where you can be fed a list, more than one event at a time. So this, you can see that it's an override. I've got to implement this process method, and it's passed in a database session, and it's passed in a list of events. And then in my code that I write, I'm processing those events. So if I'm not going to dig into this code, but it's using just very basic JDBC, but it's building up a big, it can get like 100 or 200 events, something like that. And it's building up a single big upsert, one single SQL command, and is submitting that via JDBC to the database to slam the data into these queryable tables as quickly as possible. So the interesting thing though is the actual reading by offset and all that mess, to be honest, is not something that I have to write as a developer, or you have to write as a developer. That's being handled by this system. I just implement this process method and do what I want to do with these events that I've been fed to. So in this implementation here, I'm updating, writing data to a view. Another implementation uses exactly the same kind of process method to be taking events and making those API calls. So a different event handler that's talking to some external service, pushing data to Kafka, whatever you want to do with it. You decide what you want to do inside of these projection implementations. So, as I mentioned, it's like, why CQRS? Well, I've been developing for a long time, a long time. And if you look at my bio, I'm very honest about the fact that I built systems that weren't fast enough and were brittle and broke too much, and I didn't like it. And this is why I like things like CQRS, and this is exactly why I love things like Akka, because it gave me tools to do like high performance, high reliability systems that didn't wake me up in the middle of a night and the weekend because of a production outage. I don't like having to do those kinds of things, and I want tools that allow me to enjoy my weekends, not spend my weekends fighting some type of production outage. And CQRS, often the databases were the things that were our performance bottlenecks, and CQRS really opens things up from a performance standpoint. So it's increased throughput for definitely, because it's really, you're significantly reducing contention on the database. And it's optimized for data models. And I want to go back to a prior slide to make that point. And what I mean by optimized for data models is that, say this service, some of the queries that you want to do with this service are best served by a relational tables. So you have an event handler that's feeding events to a relational table. But say you want to do other queries using something like Elasticsearch, an inverted index type of a document query or something, almost like a Google search type of thing. And I've done this kind of thing in the past myself. Or maybe use another, it might be a hierarchical database or a Mongo, or whatever you want to use. So you can have multiple of these event handlers. Some of the events, one event handler is feeding data to relational query tables, another event handler is feeding data to, say, Elasticsearch, another one's feeding data to Mongo. Whatever you want to do, you have the flexibility to do that, to do those kinds of things using this type of an approach. And with the Akka part, adding on to it, we're stateful, not stateless, and that adds to performance as well, because you're reducing how often you have to go back to the database to read from it. So this whole concept, I like to use the terms hot state and cold state. So that's what I'll kind of wrap up with here with, is that kind of taking you through an example of a stateless flow and a stateful flow. So on the top represents code. This box in the top represents the code where computations occur. The bottom represents the data, the database. And I call the top is where hot state computation occurs. The bottom is where you store things in cold state. So when you get a request in a stateless type of a system, the request comes in. That trigger is recovering the state, reading the state from the database, you're pulling it into memory, processing the incoming request, writing whatever changes are needed as a result of the processing back to the database, and then throwing the state away. And so that's the flow. And I'm not saying that stateless is a bad a bad architectural pattern at all. It's a great architectural pattern. It's extremely mature. We have fantastic tools to do these kinds of things. But when you're getting into performance types of situations, you have to consider the consequences of using this approach. And is there a way maybe to go faster? So that's the only reason I'm showing this. Not that stateful is bad in any way. It's a great pattern. Nothing wrong with it. So anyways, another command comes in, read the state from the database, get it in memory, run your processing, save it. So just repeat this cycle where we recover the state, get it in memory, but we can't keep it there because of the nature of the way the stateless systems work. So we constantly have to go through this cycle. So it's the reads that we're doing over and over. The writes are unavoidable. When you make a change, you want to get it written to a safe place as quickly as possible, within a normal transaction. So that's the stateless flow. Now let's take a look at the stateful flow. So we still have the same thing. We had the code at the top, the cold state, the data at the bottom. Same thing though. A request comes into the system and say the state is not in memory at the moment. So we have to recover the state from the database. So we read the state from the database. Now it's hot in memory. We process that request. We write the changes back down to the persistent store, the cold state. Now, if you're using event sourcing, all you're writing is like a single insert of an event. You're not updating or deleting or anything like that in tables, which is kind of the normal pattern with a CRUD type of an approach. So the next command comes in. Well, the state's already hot in memory. It's active, so we don't have to read it again. So we receive a command, we process it, we write the change. We receive the command, we process it, we write the change. So we've eliminated the read. So that can definitely take some load off the database, which helps because when you want to, if you're pushing a system fast and you want to go a lot faster, if you can take some load off the database, it's going to help you go faster. It's going to help the database go faster. So that's the flow here. So in that map-based Where on Earth demo app, it's built using event sourcing. Both there's two microservices and they both use event sourcing. But the first microservice, which is a simulator, which is kind of simulating IoT devices in the real world without actually having physical devices in the real world, doesn't have a query component. It doesn't need it. But the twin service, as I call it, it's planned digital twin. IoT devices, the backend is often called the digital twin of the physical device in the real world. But in any case, that microservice does have a view, a projection. So I want to show you this in the map one more time. That this demo, that what's happening when I'm going to create some devices. I'm going to zoom out a little bit to create. I'll create 4,000 over here. So I'm kind of, I can move around the map and I say, well, where do I want to create some devices? And I want to create, like right here. Okay. Actually, I'm going to create right here. And when I click, which I just did, that sends in a single request to the simulator service. Then it starts sending 4,000 requests over to the twin service. The twin service gets those requests and creates those events and gets them stored. And then there's a projection that's picking up those events and processing them because the data that we see in the map here is coming from the projection table. So I wanted to kind of visually watch how quickly that whole sequence of events occurred here. I can do the same thing where I can say I want to delete these 4,000 devices. And so I'm going to delete them. And so again, one request went into the simulator service. It's sending over 4,000 requests to the twin service, and now it's processing those requests and deleting all those devices. So there you go. So they're gone. So, and again, what was happening is that the events went into the event store, and then the event handlers were picking those up and making changes to the query data. And what we're seeing on the map here is data coming from the query table. So that's why I wanted to show you this this demo one last time in the presentation. Very fun app to build. So kind of wrap up, how fast is fast enough? And one thing I did, and I actually got a little bit more data today, but I didn't have time to update these slides from some recent events. But I took some data from some information about Amazon, and the number I got was that they were doing on average around $10,000 in sales per second in 2020. So I just ran a little math on that, and I assumed, and this was just me doing some guesstimation, just playing a little bit, but so all right, let's assume that every order is on average around $50. And that means, if we're getting $10,000 per second, divide that by 50, that means 200 orders per second, which is, not that high. Now, I just got some data today about, Amazon had their Prime Days, I think it was last week, and some data came through from that, and the number of orders per second, I think, was around 1800, if I remember correctly. So at a very big spike at the Amazon level, they're doing around 1800 orders per second. Now, I also played with IoT devices and said, all right, let's assume we have an IoT system with 1 million devices and say that something interesting that will actually trigger a state change happens, say, every 10 minutes. And these IoT devices, which is fairly common from what I understand, send in a message every minute. So every minute they send in, hey, I'm here and this is my state, and nothing's changed. So it's, it's just sending in telemetry messages like once a minute. But let's assume every 10 minutes, something interesting happens, which is going to trigger something in the microservice that receives these requests to make a state change, which perform a logical operation. And that only resulted in around 1700 per second. Now, another one that I think is very interesting is Alibaba. There's this annual shopping event now. It's a massive shopping event, primarily in China. It's called Singles Day, and I believe it's on November 11th every year. So they put out a statistic in 2020 that in the first 111 minutes of 11/11, they did $1.5 billion in orders. $1.5 billion in just under 2 hours. Amazing. So when he's ran a little bit of math on that, that's 223,000, almost 224,000 in sales per second. And I just did, all right, let's assume that the average order is around $25. So that still came out to be around 9,000 orders per second. So how fast is fast enough? Well, this is kind of in the thousands per second range, not in the millions per second range. And this is one of the biggest shopping days of the year. So here's the GitHub repos, and I'll share these slides. I'll give you guys this, a link to the slides that the Mindset can share with you later. But it's just in GitHub. My user is McKee H3, and it's the repos are we-sim and we-twin. If you're interested to grab those. The other demo, this Akka cluster visualizer, also known as a crop circle, same GitHub, my user, and it's Akka-cluster-Kubernetes, and then there's -simulator and -visualizer. I always say these readmes, there's a lot of readmes, they're never done, but I think they're in reasonably good shape. And really want to thank for listening in, and certainly thank my hosts here, Mindset, for giving me this opportunity to speak to you. And I hopefully we have some time for some Q&A.
Yeah, thank you, Hugh. Thank you very much. It was really interesting to see the demonstration and the both of this application. I don't know if there is a live question, but I had two questions. The first one was about the instance activation time when it receives a request to handle, and then receive a lot of requests, and for sometimes it doesn't receive any other requests. How this is handled? Is it with Akka, with Kubernetes? How you can set the time? Is it something that the developer can should worry about, or is it something that handled automatically with Akka or Kubernetes?
Yeah, there's really, you're talking about the entity, right? The flow there. Yeah. So there's really one main configuration setting that might be of consideration. There's of course a default setting, but you can override it, and that is how long should an entity wait before we call it passivates itself. And I show this in this demo here, where what you can see as this thing's running is that you can see things are moving around, and where you'll see some things kind of go away. And those are entities that are shutting themselves down. They're passivating because they haven't received a message for a while. So I had to fine tune that configuration setting based on, the rates and everything that's going on here, but I had to shorten it a bit so that I could make it, where you would see something happen, and I could explain it. So it's really dependent on the behavior of the system. Like if it's an IoT system and every single IoT device is receiving telemetry messages once a minute, which is actually what I did in this demo, that there's 240,000 now devices. So every minute, the simulator service is sending 240,000 gRPC telemetry messages to this other microservice, and it's just saying, hey, this is a message from the service. Nothing's changed, but I'm just sending you a message. So basically all 240,000 of those entities, let me go back to this demo. If I could, and you can't, but there would be 240,000 of these blue circles in this, from the other system. They're all alive at the moment because they're receiving messages once a minute. And I had to make sure that the timeout period was longer than 1 minute. So I set it to like 2 or 3 minutes or something like that. But if these guys don't receive a message after that time, say I shut down the simulator service that's sending messages, then everything will shut down within a few minutes. So it's really dependent on the behavior of how often messages coming in, that type of thing. So like in a shopping cart, how long do you want to wait in between messages from the user? Maybe it's more like 5 minutes or something. And then the other part though is that recovering the state from the database when it's not in memory is quick as well, because there's two things that are used. One is that like a shopping cart's not going to have a lot of events, maybe 10, 5, 15, 20 events per shopping cart, because there's not that much data and there's not that many things you do to build up a shopping cart before you say buy or before you forget, abandon the shopping cart. But in things like a bank account that would have a long history of events, we're not going to recover all the events. And there's a thing called snapshots that have, like, a snapshot is done periodically, like once a day or once every 1,000 events, or that's configurable as well. So the idea is that for long history entities like a bank account, to recover its state, you go to the last snapshot and then any events that happen after that. So typically you're looking at maybe 10 milliseconds to bring an entity to life somewhere in the cluster. Fairly short, and then once that read's done, then you don't have to read it anymore.
Okay, great. I hope that we have just some time for one last maybe question. The question was about the offset. So when you showed the event handler, the question was about when there is a failure on the event handler. How is the offset how you can manage to save the offset? How this is saved before there is a failure in the event handler?
Yeah, that's a really good question. Yeah, go ahead. Yeah.
So when you recover it, it starts from where it was where the failure happened.
Right. So really good question, and the answer is there's a number of different approaches where the offset is stored, and it's very much like how Kafka works. For example, Kafka is very read by offset, also consumers. So with Kafka, if you use Kafka, you probably had to consider the offset as well. But in here, the offset is managed by Akka, but the question is the offset stored within the same transaction that the target data is being stored? So and that varies as well. If the target database is JDBC, then the offset is stored with the same transaction as the data being stored in the queryable view, the queryable tables. If you're doing something like Cassandra, then the offset is stored separately in a separate transaction. So the differences between exactly once processing of events versus at least once processing of events, which means that you have to know, is your projection at least once processing or exactly once processing? Exactly once is easy. At least once is that you're guaranteed to see every event, but you may see events more than once. So the operations performed by processing the events have to be idempotent, meaning that when you repeat that same event again within an event handler, the outcome needs to be the same. You have to consider that. Welcome to the distributed world, though. This is the way things work in the distributed world.
Yeah. Okay, great. Thank you very much. I think our time is up. So I don't know if there is any other question. I don't see any. So thank you very much, Hugh. Thank you for everyone. We will wrap up this webinar. We will try to organize other webinars, not during the summer because there is other vacation. There is a lot of vacation during the summer, but starting September. So stay tuned. And we will at the end we will send you the slides and the links to all the application that you demonstrated for this webinar. So thank you very much. Have a good evening, everyone, and see you soon. Bye.